So you know what you're going to go with study it up to the test.
What time's your test?
8:30 tonight. I'll follow in the morning.
Most of them are like,
Yeah, it's like 8.
it's like 8 or 9.
Yeah, it's really, it's like 8:30 to like 10:30 or something.
That's terrible. It's okay. It's all right.
It's for something.
Really, how do we go up after boyfriend with math and stuff?
Huh?
How do we go up after boyfriend with math and all that? We just saying that so we didn't have to go ahead. Okay.
We made up for
He made up for it?
my boyfriend.
And
So he figured out his mistake.
I did. Okay.
Shocked.
That's not how it works, but yeah. Well, yes, I'm okay.
See?
Okay. So, eigenvalues, eigenvectors, similarity, and diagonalizability. That's what the homework is all about. So, what is an eigenvalue? So we say that if there exists a non-zero vector x such that a times x is equal to a multiple of x, then we say that lambda is an eigenvalue of a. And x would be the corresponding eigenvalue. All right, so sometimes this is called a characteristic value for the matrix, and this would be characteristic vector. I believe eigen is German. It's characteristic or property of intrinsic value. Okay, so this is important because you would, given a linear transformation that's square, right? That corresponds to a square matrix. We would love to represent that transformation as a matrix that's as simple as possible. And if you can create a basis using eigenvalues, the matrix representation of the transformation is especially simple. It becomes a diagonal matrix. So, we get to choose what our basis is for vector spaces. And here, it's important to be able to create a basis using eigenvectors. So that's why this simplifies the matrices. And geometrically, what does this mean? How do you interpret this? Well, suppose you're in R3, correct? And you have a transformation, say a projection matrix, which takes vectors as just vectors, multiplies them and projects them onto the plane, some sort of subspace here. Okay. What would you expect the eigenvalues of this transformation to be? Well, consider two cases. Suppose you're a vector that's already in the plane. Then, if I project that vector that's in the plane onto the plane, I just get that vector back, correct? And suppose this is a non-zero vector, and you can definitely find a non-zero vector. So you see that transforming this vector that's in the plane just gives you a multiple of that vector, and the factoring multiplied by is 1. So we would say that 1 is an eigenvalue for this projection matrix. And x would be an eigenvector. Well, what's another important case? Well, suppose you take a vector, let's call it y, that's perpendicular to the plane. So when you do the orthogonal projection of that vector onto the plane, what will you get? 0, right? And so, but we can express this as 0 times y. So you see that we can say that 0 is an eigenvalue for this matrix and y is an eigenvector. So there are some kind of, basic transformations where you can actually see what you can interpret, have a geometric interpretation of an eigenvalue and eigenvector. So what about a rotation by pi radians, right? So it's going to be -1, 0, 0, 1. So here we're taking stuff in the plane and we're rotating it 180 degrees. And so x rotates. And you get something like that. 180 degrees, it's a straight edge. What would the eigenvalue for this matrix be? If you rotate the vector x by 180 degrees, what do you get? Well, you get a vector that has the same length, but it's pointing the opposite direction, right? So it's just the negative of the original. So geometrically, we can see that that a -1 is an eigenvalue for this rotation matrix. And what else can we say? Well, what are all the eigenvectors? That's the whole plane, right? Because you can take any vector, I don't care what it is, rotate it, and you get -1 times that vector. So the eigenvectors is all the vectors. Technically, eigenvectors are non-zero, right? So I guess you can exclude 0. But we sometimes talk about eigenspace. So that's a subspace, right? And to be a subspace, you have to have the 0 vector. So if you take the set, so let's just say it's the eigenspace associated to eigenvalue lambda is the set of all eigenvalues, vectors I mean, for lambda, and the 0 vector itself, right? So we just throw the eigenvectors together with the 0 vector, and then you have a subspace, an eigenspace. Okay. All right, so the question is, okay, so we want to find these eigenvalues and eigenvectors for a square matrix. So how do we go about that? Well, the criteria is spelled out right here, actually. So what we can do is say, all right, let's just bring this over to the other side, or I'll do it the way your notes did it, so they brought that over to the other side. And that's the 0 vector. And then let's just insert an identity matrix here, so it's still identity times x is x, that doesn't change anything. And then factor out the x. All right, so now remember that x is a non-zero vector. Right, that's the criteria for finding eigenvalues. We have to have a non-zero vector that satisfies this equation. So here we have a homogeneous equation, right? We have 0, the matrix times x is 0. So we know that, so how can we guarantee that we have non-zero solutions to this equation? Well, if the determinant of this matrix were non-zero, then we know that there's only one trivial solution, so we wouldn't get a non-zero solution. But if we can find lambdas which make the determinant of this matrix 0, then we know we have infinitely many solutions, including non-trivial then we know we have an eigenvalue. So you choose the eigenvalue, you find the eigenvalues by computing the determinant of this matrix where lambda is unknown. And when you do the determinant, what you're going to get is a polynomial. So this is called the characteristic polynomial. So if you have a 2 by 2 matrix, what degree polynomial would you get? 2. If you have a 3 by 3 matrix, you get a 3rd degree polynomial and so on. Right? We compute this polynomial, we set it equal to 0 because we want the determinant to be 0 to guarantee non-zero solutions here. And then you solve for lambda, and the solutions you get are the eigenvalues. So how many eigenvalues are you going to have? What's the greatest? So if you have a n by n square matrix, what's the greatest number of eigenvalues you could have? N. But you could have less, right? And will your eigenvalues necessarily be real numbers? No. No. When we get a polynomial, we're not guaranteed real roots, right? We can have complex. So, I mean, if you, like, what would be, if you imagine a rotation by 90 degrees, can you imagine a vector that you rotate 90 degrees and get a multiple of that vector? No, there's no such thing, right? No vector, when rotated 90 degrees like this, will be a multiple of itself. So such a matrix would not have real eigenvalues. It would have complex eigenvalues. Okay. All right. Now, if you find the eigenvalues, how would you find the corresponding eigenvectors or even eigenspace? Well, once you have an eigenvalue, you can plug that number in and solve the system. So the eigenspaces corresponding to lambda is exactly the null space of this matrix. Right? It's the set of all solutions to this homogeneous equation. All x's which satisfy. All right. Now, okay, so now let's look at some examples. So suppose we have a matrix A. So we're going to work with properties. I'm trying to mimic problem number 2 in your homework. So suppose we have a matrix that has eigenvalues. A is a 3 by 3 matrix with eigenvalues of negative 2, 1, and 4. Okay. All right. Now, okay, maybe we should start with some theory. So, if you have distinct eigenvalues, right, so you have 2 different eigenvalues. What can I say about the corresponding eigenvectors? What important thing do I have to know? So, eigenvectors for distinct eigenvalues are linearly independent. This is key. Why is this key? Well, because, look, for example, if that's true, right? I have three distinct eigenvalues for this 3 by 3 matrix. I know that the 3 associated eigenvectors are linearly independent. And so if you have 3 linearly independent eigenvectors for R3, you can create a basis. Okay, so that's the key. That if you're in the business of finding a basis for your space consisting entirely of eigenvectors, then you better have as many linearly independent eigenvectors as you have dimension. Right? So this is important. I mean, that we need this linearly independent eigenvectors in order to create a basis. And the proof here is inductive, but I won't go through the clearly. So suppose we have x1 as an eigenvector, right? It's a set containing one eigenvector is automatically linearly independent. It's a non-zero vector. It's an eigenvector. So what if you say that, okay, well, suppose that we have k linearly independent eigenvectors. Can we show that the k plus 1 eigenvectors, so these are eigenvectors corresponding to distinct eigenvalues. So this is associated to lambda 1, lambda 2, lambda k, and no 2 lambdas are the same. They're all distinct eigenvalues. So can I show that if I now throw in an extra eigenvector for an eigenvalue distinct from all these, how do we show that we get a linearly independent set of vectors? Well, okay, so you check for independence by doing the standard thing of forming a linear combination of your vectors. And setting that equal to 0. And solving for the coefficients, right? But now imagine we multiply both sides by the matrix A. Right? So that's these are the eigenvectors for matrix A. And once we do that, we get I know you guys love proofs. But we get, because this is an eigenvector, A times x1 is lambda 1 times x. So we just get a scaled version of the vector. Oops. And of course that's 0. Okay, so now what you do is you multiply the original equation by lambda k plus 1, the k plus 1 eigen value. So right now, you take this equation and this one and you subtract. Okay, so then you would get C1 lambda 1 minus lambda k plus 1, and so on. Of course, this subtracts to 0, right? It's exactly the same term. Right, so what do you know about these differences? Well, because we have distinct eigenvalues, these differences are never 0. Right? So we have non-zero numbers. Non-zero because the eigenvalues are assumed to be distinct from each other. All right, but then we have a linear combination of k linearly independent eigenvectors. That was our, gosh, you guys don't, when I say inductive hypothesis, okay, well, but If these are non-zero and we do have k linearly independent vectors, then we know the coefficients have to be 0. Right? The c's have to be 0 by definition of linear independence. And of course, if these c's are 0, then since this is a non-zero vector, this has to be 0 as well. Anyway, okay, I shouldn't have done that. This is important. Eigenvectors for distinct eigenvalues are linearly independent. Okay. All right. So I'm guaranteed that I'm going to get three linearly independent eigenvectors for this matrix. So we have distinct eigenvalues. All right. What can we say about the eigenvalues of A inverse?
Of what, I'm sorry?
A inverse. Yeah. Right. So first of all, how do I know that this matrix is invertible?
Because one of them are not.
Right. So right. So the idea is that if you're, the determinant of the matrix is, here's a nice theorem. The determinant of the matrix is equal to the product of the eigenvalues. Okay, I won't. So if one of your eigenvalues were 0, then the determinant of your square matrix is 0, and that's not invertible. But if none of the eigenvalues are 0, then what can we say? Well, then the matrix has determinant that's non-zero, and the matrix is invertible. So it's legitimate for me to ask for the eigenvalues of the inverse, because I'm guaranteed that it exists as none of the eigenvalues are 0. Well, okay, so if you wanted to find the eigenvalues of the A inverse, how would you set up the problem? Well, you would say, okay, I'm going to find the determinant of, let's call it mu for the eigenvalue, I minus A inverse, correct? And we would set that equal to 0 and solve for mu, to find the eigenvalues of the inverse. Now, notice that I can then I can write the identity as, say, A times A inverse, correct? And then I can factor out A inverse. So you have mu A minus I times A inverse. And now you have a product of two matrices, and he's finding the determinant. So use properties of determinants. Oh, hold on. Let me factor out a mu. How about that? I'm going to factor out mu, a negative mu, just to make it clear. Okay. So you get 1 over mu I minus A. We have negative mu times A inverse. And then use properties of determinants. All right. Okay, so then we have the determinant of some number times the matrix. And let's, this is a 3 by 3 matrix. You get negative mu to the power 3 by properties of determinants. All right, and so what can I say about the determinant of the A inverse? Well, for sure I can say it's the reciprocal of the determinant of A, and that's going to be non-zero. This is not 0. Right? It's not 0 because A is invertible. What about, is this possibly 0? And oh, I should have done it the other way. Okay, that's fine. It's non-zero. Just let's pretend it's non-zero for a second. So this would have to be 0, right? But then, isn't this the way we would find the eigenvalues for A? So we would have to say that 1 over mu is an eigenvalue for A. So this means that the eigenvalues for A inverse are just the reciprocals of the eigenvalues of A. So the eigenvalues for our matrix A inverse is -1/2, 1, and 1/4. Now you could have done something concrete, because what's the simplest matrix you can think of with eigenvalues -2, 1, and 4? What's the simplest matrix you can think of that has those eigenvalues? Diagonal matrix, right? So if we just for a second said, well, suppose that A is diagonal, we know that finding the inverse of this matrix is especially easy because it's diagonal. We just take the reciprocals. And then you see that the eigenvalues for this matrix are the reciprocals. All right. So now suppose we ask...
Sorry, what you did is you just found the inverse of that matrix C then?
Yeah.
Okay.
Yeah. And of course, the triangular or diagonal matrix, the entries in the diagonal are exactly the eigenvalues. To remind you. All right. Well, suppose next we want to find the eigenvalues of, say, matrix B, defined as A squared minus A minus 6i, right? Now, one thing we could do is quite easily just see what the eigenvalues would have to be, right? Without really proving, you know. So I would say, okay, A is this diagonal matrix. Squaring diagonal matrices is easy. We just square the diagonal entry, so this is A squared minus A so this is something you can always do in your homework, right? Just you choose a specific matrix, diagonal matrix to see what the eigenvalues have to be. And we get 6, 0, 1 minus 1 minus 6. Yes. And then we get 4, 16 minus 4 is 12, minus 6, 6. All right. So you see that B would be a diagonal matrix with the eigenvalues 0, negative 6, and 6. All right, but if you want to be slicker, more mathematical, like, because here, how do I know that, you know, I mean, there's theory that will tell us that just using this diagonal matrix works, but how do I know that, you know, A is diagonal, and if it's not, how am I guaranteed that it'll still have, that B will still have the same eigenvalues? Well, so we can get more mathematical. So we can do the following. Suppose that x1, x2, or suppose that x is an eigenvector of A. Okay. And then let's multiply that eigenvector by matrix B, which is the same thing as multiplying by that polynomial in A.
Les, what if says that they just want the eigenvalues? Do you want to pull those values out of the matrix then? Or do you just think we should leave it in the matrix?
No. Specify. You just write a sentence. The eigenvalues of B are 0, negative 6, 6.
Okay.
So it's easy for your grader.
Yeah.
Your grader would be like, wait, you know,
Okay.
where's the answer?
Yeah.
I see the matrix, but
So pull it out.
Yeah.
Okay.
So okay. Multiply through. Okay, so what's A squared times x? Remember, x is an eigenvector of A. What would that be? Well, it would be, okay, A times x is lambda x, where lambda is the eigenvalue for this eigenvector. And then we have a times x is lambda again, so we get lambda squared x. Here we get a times x is lambda x, and this is simply 6 times x. And notice that you can now think of this as lambda squared minus 6 times x. So now check it out, right? We have b times x equals a multiple of x. So if x is an eigenvalue of A, it seems, an eigenvector of A, it looks like x is also an eigenvector of B. And what would the eigenvalues be? Well, what were the eigenvalues of A? Remember, lambda is an eigenvalue of A, right? So in the case where lambda is -2, you would have b times x equals 4, 2 minus 6. So 0 times x. So 0 is an eigenvalue of B. In the case where lambda was 1, you have b times x equals, replace lambda here, and we get -6 times x. So -6 is an eigenvalue for B. And in the case for lambda is 4, b times x equals, you have 16 minus 4 minus, so that's 6x, right? So 6 is also an eigenvalue of B. So that's the kind of more, I don't know, cooler way to do it. And so what about finding the eigenvalues of b squared or something? So we want to find the eigenvalues of like this animal, right? Same procedure. You can even, assume that A is diagonal, and then you define B so you can compute B directly and see what you get. But we can also say, okay, suppose x is an eigenvector of A, then we get b squared x minus. And now, okay, so let's just do an example where lambda, so this is like eigenvector 1 for matrix A associated to eigenvalue 1 of A. So -2 is the eigenvalue, first eigenvalue of A. Okay, well, what's b squared times x1? Well, it's 0. Well, because b times x1 was 0. So it's just a 0 vector. And what's A inverse? A right inverse. Okay. So, I can prove that to you. How do I know that? How do we know that if? Gosh, okay, this is just a slide, I guess. If x is an eigenvalue of A, eigenvector of A, and A is invertible, then x is an eigenvector of A inverse. So, right, so we proved that the relationship between eigenvalues of A and A inverse are reciprocals, right? They're reciprocals. But how can I prove that? Well, suppose we have A times x, our eigenvector of A, equals the eigenvalue times x. Just multiply both sides by A inverse. Right? You get identity times x equals lambda A inverse x. And you divide by lambda. Now, A is invertible, so we know lambda cannot be 0. We can't have 0 eigenvalues for invertible matrices. So it's fine to divide. And there we go. Right? What we have is A inverse times a vector x equals a multiple of that vector x. So x is also an eigenvector of A inverse. So I forgot to mention that. So A inverse times this eigenvector will give you the reciprocal of the eigenvalue -2. And then you multiply by A inverse again, and you get 1/4 x. So what we have found here finally in summary is this matrix times x is -1/4 times that. So we see that -1/4 is an eigenvalue of this matrix. Right, because the matrix times x is a multiple of x, so it's an eigenvalue.
Got a question here?
Yeah.
Right here.
Yeah, so you're just pretty much squaring the eigenvalues you got from A inverse in this case.
Yeah, yeah. Because it's, so x1 is an eigenvector for A inverse, right?
Yeah.
With eigenvalue -1/2. And then since you're squaring it, it'd be that eigenvalue times itself, that's right. All right. And then suppose we define matrix C. And I'm going to write A plus 2i, A minus I, you see y, and A minus 4i, right? Right, I'm just using the eigen, like if I were to write out the characteristic polynomial for this matrix, right, if the determinant of lambda I minus A, right, it's some polynomial, set it equal to 0, I would get the following: lambda 2, lambda -1, lambda minus 4. Right, because then this gives me, and possibly some constant here I forget. But the idea is that, right, this must be the these factors must be the characteristic polynomial because the eigenvalues are -2, 1, and 4. And we got, those are the values that make the polynomial 0. And this is factored in a similar way, except I replace lambda with A. Okay. It's an important theorem we probably will get to later. All right, so what are the eigenvalues of matrix C? Well, okay, well suppose we take the first eigen value, the vector for matrix A, so x1, right? It's associated to this eigenvalue. What will this be? Well, okay. These things commute, right? Because A and I are commutes, we can rearrange the factors. So I can write this as A minus I. X1, right? Okay, multiply through here. I'm just focusing on this factor. You would get A x1 plus 2 x1. And what is A times x1? -2 times x1, right? Because the eigenvalue for x1 is -2. So that would be 0. So this would be 0 vector, so the whole thing is 0. So it looks like 0 is an eigenvalue of C. And you repeat the process, right? So if I took the second eigenvector for A, associated to this eigenvalue, and I say C times X, by rearranging I see that over here, when X gets multiplied by this, you get 0. Right? Because you get A times X2 minus X2. But A times X2 is just 1 times x2. So you get 0 again, and the whole thing is 0. And likewise for the third eigenvector associated to the eigenvalue of 4. You get 0 times x2. So it looks like this matrix just has one eigenvalue, so 0. And how do we know? So here's a simple matrix that has those eigenvalues. It's the 0 matrix. But does C, the matrix C, have to be the 0 matrix? Well, let's think about this. We said that we have distinct eigenvalues, so x1, x2, and x3 are linearly independent eigenvectors. So they form a basis for R3. And if you know what the matrix C does to the basis elements, you know what the matrix C does, period. Because every vector in R3 can be expressed as a linear combination of these basis elements. Right? So if we know that the matrix, when it multiplies the basis element, always gives you the 0 vector, then it must, since any other vector can be rewritten as a linear combination of those. Right, so here's some vector expressed as a linear combination of the basis consisting of the eigenvectors. You just get 0. And that's only true if the matrix itself is 0. So the C has to be 0 in this case. So, all right, well, Josh, what's next? Yes, this important question of diagonalizability. So, okay, well, in similarity. Okay. So let's, for the sake of illustration, suppose we're working with 3 by 3 matrices. And we have eigenvalues, lambda 1, lambda 2, lambda 3. And then we have eigenvectors, and that's just for now assume they're distinct. I mean linearly independent, sorry. Should I use that? Yeah. Eigenvalues, and these are eigenvectors, and they're, let's just assume they're distinct, linearly independent. It's not necessarily the case. I'll show you examples, but it's not. So what would happen if I multiply x1 by matrix A? I would get lambda 1 times x1, and so on, right? Because these are eigenvectors, the eigenvalues. And then let's write this as a matrix equation. Express that as this is a matrix equation. We would have A times the column consisting of the first eigenvector times column. The next column is the next eigenvector. This is the third. Okay. What would I get? Well, A times x1 gives you a column which is lambda 1 times x1. A times x2 gives you lambda 2x2, and so on. And this would be lambda 3x. Now, define the matrix P to be the matrix whose columns are the eigenvectors, the linearly independent eigenvectors. And then we can write this as AP. Now, this is not so obvious, but you can write this side as P, but you can confirm times the diagonal matrix consisting of eigenvalues. So so multiplying this matrix with this column gives me a linear combination of the columns. You would have lambda 1 times x1 plus 0 times x2 plus 0 times x3. So that would give me the first column here. So we see that the right-hand side can be expressed as P times a diagonal matrix. So define this to be a diagonal matrix. And there we go. And then if you multiply both sides by P inverse, and how do I know P inverse exists? Well, we said that our eigenvectors are linearly independent, so that's invertible. Multiply from the left by P inverse, and you get the diagonalization inverse of it, right? That's how you diagonalize the matrix as possible. So to diagonalize a matrix, number one, you find eigenvalues. Number two, you find eigenvectors for those eigenvalues. And if you have enough linearly independent eigenvectors, right, to create a basis, you stick them in a matrix, P, and apply this recipe. And you're guaranteed that the diagonal matrix you get consists of the eigenvalues. All right. So are all matrices diagonalizable? Well, zero matrix is already diagonal. Okay. Well, the answer is no. So here's an example of a matrix that is not diagonalizable. So example of non-diagonalizable matrix. All right, so here's finally we get to compute eigenvalues and eigenvectors. All right, so let's do it. Let's find step one. Let's find eigenvalues. So we compute the determinant of lambda I minus A. We set it equal to 0. Get the characteristic polynomial, set to 0, and solve for lambda. So let's see, we get the determinant. We have lambda minus 1, right? Then minus that entry. Oh, maybe I should write it out if you haven't seen it before. So, okay. Lambda times the identity you agree looks like this. Here's A. Then we have lambda minus 1. We have 0 minus 1. Minus negative 4, positive 4, and lambda minus 5. And that's set equal to 0. Complete the determinant, and you get lambda minus 1 times lambda minus 5, negative 4, minus a negative 4 is plus 4. And you see that you get a second degree polynomial, and you want to solve for lambda, so let's just multiply everything out, and either factor or use the quadratic formula. And I believe this does factor, right? It's a perfect square. So lambda minus 3 squared is 0. So the only eigenvalue is 3. Now, if we had two distinct eigenvalues, what can I say about the corresponding eigenvectors? Well, they're linearly independent, right? Because if they were distinct, right? Then I know that I would have two linearly independent eigenvectors, and therefore I could follow this procedure and diagonalize my matrix. Here I only have one eigenvalue. But don't be fooled. It's possible that you have one eigenvalue, but two linearly independent eigenvectors. So we still have to go find the eigenspace and see, or eigenvectors to see if we have two linearly independent eigenvectors. So step 2, let's find the corresponding eigenspace or eigenvectors. find eigenvectors. Eigenspace for this sole eigenvalue. Right. So we said that the eigenspace is going to be the null space of this matrix lambda I minus A. Right. So, and that matrix. Right. I had it here already. Just replace lambda with 3, and you get 2, -1, 4. Now, if I start reducing this matrix to find its null space, and I get the identity matrix, I did something wrong, right? Why is that? Well, we chose lambda exactly for the reason that it made this determinant 0, so there's no way you should be able to reduce this to the identity. Okay. But here we see that this is quite simple there. And so, remember that this is, we're finding the null space, so it's really, if you'd like, this, you augment the matrix with 0 on the right-hand side, right? So then you have like x, y on the right-hand side. So this says 2x minus y has to be 0. Okay, so y is equal to. So give me an eigenvector. Give me an example of an eigenvector. Well, it's the null space, so the null space has to satisfy this equation. So we have, like, x could be 1, correct? Y would have to be 2. Now the eigenspace, if you'd like, associated to this eigenvalue of 3, it would be the set of all eigenvectors and 0 vector. But notice that we can easily say, well, if x is t, right, y would be 2t, and you see that the set of all eigenvectors and 0 vector are multiples of this 1 vector. So we say, so this is the basis for the eigenspace. Okay. Right? It's one-dimensional, right? We only have. So we have only, we can't find 2 linearly independent eigenvectors because the eigenspace, the sole eigenspace is one-dimensional. So there's, I cannot find the basis for R2 consisting of eigenvectors, therefore I cannot diagonalize this matrix. Okay. There's, this matrix, it's not possible to find invertible matrix P such that P inverse AP gives me diagonal matrix. Not possible. Right. And so now we get to the criteria by which we know whether you can diagonalize the matrix or not. It's simple, right? As long as, so if you have an n by n matrix, we know it's diagonalizable if and only if it has n linearly independent eigenvectors, because you need a basis. So A is diagonalizable. And only if. So this is an n by n matrix, my bad. A has n linearly independent eigenvectors. Because then we have a basis consisting of eigenvectors. So if you have a matrix, right, and it has 3, so let's say, so n by n matrix, and it has n distinct eigenvalues, how many linearly independent eigenvectors does it have? As many, right? Because of all distinct eigenvalues, you have linearly independent eigenvectors. So a matrix with distinct eigenvalues, all distinct eigenvalues, right, is necessarily diagonalizable. And so, all right, so let's do a big example here. Yeah, let's do this. So here's the matrix. So just the full procedure for this 3 by 3 matrix. So here's it. 4, 0, 0, -3, 1, 3, 3, 3, 1. And we want to diagonalize this matrix. So do you want to know the neat theorem, I guess? We said that the determinant of the matrix is the product of the eigenvalues, right? It also turns out that the sum of the eigenvalues is the trace of the matrix. So it's interesting. So the product of the eigenvalues, well, I don't know what the determinant is, let's see. It's 1 minus, so 4 times -8. The product is -32. And the sum of the eigenvalues will have to be the trace, so you add the diagonal, that should be 6. That's interesting. All right. But step 1, right? We need to find eigenvalues. So we create the characteristic polynomial set n equals 0, we solve for lambda. So we get lambda minus 4, 0, 0, 3, lambda minus 1, beta 3, 3, and lambda minus 1. Okay. So this is, we're going to do cofactor expansion to determine it along the first row, because these are a bunch of zeros, so I get lambda minus 4 times lambda minus 1 times lambda minus 1 minus 9. And it's practically factored, right? I'm not going to multiply it out. I'm just going to use the fact that this is the difference of 2 squares. So we can factor into conjugate. So lambda minus 1 minus 3. Lambda minus 1 plus 3. There you go. So it looks like our matrix has 2 eigenvalues, or sometimes you would say the 3 eigenvalues are -2 with algebraic multiplicity 1. And then lambda is, the other 2 eigenvalues are 4 and 4. Or we can say that the eigenvalue is 4 with algebraic multiplicity 2. So lambda 1, lambda 2, and say multiplicity 1, multiplicity, I read that, 2, because of course it's a factored plus. All right, so now for each eigenvalue, we need to find eigenvectors, or eigenspaces. And again, it's possible that, right, okay, so if this eigenvalue has algebraic multiplicity 1, this is a factor just once, the eigenspace is going to be one-dimensional. And if the multiplicity is 2, the eigenspace could be 1 or 2-dimensional. We don't know. But it's, the dimension of the eigenspace is at most this number. So we said, yeah, I'm not going to introduce it to a knowledge of the lecture from the professor. So for lambda, the eigenvalue of -2, what is the corresponding eigenspace? Well, it's the null space of this matrix. -6, 0, 0. And usually this is short work, right? Because you just row reduce. And you know that you have to get at least one row of zeros, so. I won't go, I won't bother you with the details. So, okay, so that's one. Let's zero that out, zero that out. Oh, okay, there you go.
So
All right, there you go. If I reduce, I get something like that. Well, exactly that. All right, so again, just remember that this is, we're trying to find this set of all solutions to the homogeneous equations, x, y, z, right hand side. So we get that x has to be 0. Then we get y plus z has to be 0. So the eigenspace is going to be, well, x has to be 0, and z equals the negative of y. So if z is 1, I'm sorry, if y is 1, z is negative 1. And any multiple of that would be an eigenvector, so it would be 0. So you see that indeed this is an eigenvector, just a particular one. And this is the eigenspace, it's the span of this vector. Okay, so as advertised, we have the eigenspace has dimension 1, so one basis element. Next, we find the eigenspace for lambda equals 4. Again, we're just looking for the null space of the matrix. 0, 0, 0. 3, 3, 3, 3, positive. Okay. So this reduces nicely as well. Its reduced form looks like this. So this says that x plus y minus z equals 0. Geometrically, what is this in R3? What's the geometric object? It's a plane, and the plane is two-dimensional, right? So it looks like our eigenspace is two-dimensional. And so this would be, let's say, if we let x and y be some parameters, so I won't have enough space, I don't think. So the eigenspace, lambda equals 4. So we can let x be t, let y be s, and z would have to be t plus s. So right, you can write this, that eigenspace consists of all combinations of these two vectors. Okay. Right, so, okay, so I know that these eigenvectors are independent because they belong to distinct eigenvalues. And I see that these are independent as well, because one is not a multiple of the other. So what we have found is 3 linearly independent vectors, eigenvectors. We can use that as a basis. So my matrix P consists of columns which are the eigenvalues of vectors. So 0, 1, negative 1. I could have chosen any multiple of this except obviously 0 vector. And then these. I just need to find some basis, right? This basis is not unique. That's my matrix P. I just stick some of these eigenvectors into columns. And then we have to find P inverse. So you reduce or whatnot. I believe P inverse is 1/2 on wrote the order of the eigenvectors differently in that example. So I get reduced by calculator, or invert by calculator. 0, 1, 0, 1, 0, 1. Okay, so 1/2, 1, 1, negative 1, 1, 0, 0, negative 1. Sorry, that was 2. 2, 1. Okay, so that's the inverse. And then I don't even have to do any multiplication. I'm just presenting a solution for the grader. So I know that the diagonalization will look like this by our formula. P inverse times matrix A times P equals the diagonal. So you get P inverse. You get matrix A. And it's, of course, you can check that this is correct, right, by actually multiplying this out. P. Right, so if we multiply this up, I'll have to get a diagonal matrix. And what would the diagonal entries be? What would go over here? So, okay, this was the eigenvector for the eigenvalue of, was it -2? -2. And these were the two linearly independent eigenvectors corresponding to lambda equals 4. So, the order of the eigenvalues here, of course, just multiply it out and check, but you're going to, since this is the first the first column, right, we get -2 for the first diagonal entry. And these two columns are eigenvectors for lambda equals 4, so you get 4 and 4. It's that order. You have to keep that order correct. So now your matrix is diagonal. There's applications for this. Right, so the idea here, the big idea was that if this represents a linear transformation, you can find a basis where the matrix representation is a diagonal matrix that makes computation simple. How much time do we have? About 8 minutes. All right, so let's look at this relationship. And this is if two matrices are related in this way. Okay. So there's a more general thing here that if we can transform one matrix, so we have AP equals PB, right? Where P is invertible. So essentially what this is that these are two matrices representing the same linear transformation but relative to different bases. And if I multiply those sides by P inverse, you get this relationship. And if you can find an invertible matrix such that this is true, what do we say about A and B? A and B are then called similar matrices. So if we can find an invertible matrix such that this is true, then we say that A and B are invertible. Right, similar. It's a similarity relation. It's the similarity relation. Right, and what you want to be aware of, especially because it makes one of the homeworks really easy, I forget which number, but it's the question of, are these two matrices similar? You want to be aware that we have similar matrices, they have some things in common. There's some things that are invariant. It's the same for both. So let's just list some of the invariants for similar matrices. If A and B are similar, then what do we know? So A and B have the same determinant, right? Now this is really easy to see, right? Because if you have, let's see if we pick this determinant of B, and we know that B can be expressed as P inverse AP, because A and B are similar. These properties of determinants and the determinant of P inverse is just the reciprocal of the determinant of P. So you see what's going to happen. These cancel. You get the determinant of B is the determinant of A. So these are, let's call these similarity invariants. So these can be used to fish out matrices which are not similar to one another. The converse of that problem is to, in general, it's hard to say whether two matrices are similar. But if some of the invariants don't hold, then they cannot be, right? So these invariants are used to fish, to eliminate pairs of matrices which are not similar. What's another one? Of course, obviously, they're both, either A and B are both invertible or not. They're either they both have inverses or they both don't have inverses, right? If they're similar. They have the same rank. And so on. Let's see. They have the same nullity. So all these are invariants. Because again, really the way to think about this is that these matrices represent the same transformation relative to two different bases. So all this geometrically the same type of stuff. The traces are the same. So if you add the diagonal entries of A and B, or the diagonal entries of A and diagonal entries of B, they should be the same. They have the same characteristic polynomial. They have the same eigenvalues. You can especially see this if your A and B are both diagonalizable, right? Then you can turn one into diagonal matrix and the other one into the same diagonal matrix, so the same eigenvalues. And finally, the eigenspace dimension is the same. But right. So, like for example, if I start, have same dimension. And again, this is if A and B are similar, then you can say this. But because you can say this about two matrices, if you can say this about matrices, you're not guaranteed that they're similar. So for example, is it possible that these matrices are similar? Well, the easiest thing to do is just to realize that the trace of this matrix is 6, the trace of this matrix is 7. If they were similar, then they would have the same traces. Or maybe in an example, you might find the eigenvalues of one matrix, find the eigenvalues of the other. And if the eigenvalues are not the same, there's no way the matrices could be similar. And so, okay, that's all I got.